So looking at the 9394 homework, which is, due tonight, along with 13.1, 13.2. So this is the 9394 number 5. Okay.
Oh, it says problem 5 homework receipt one.
Okay, good. Okay, since 2010, when there were 900,000 cases reported, each year the number of new cases of equine flu has decreased by 40%. So we have fewer cases each year, right? We're going to let P sub n represent the number of new cases of equine flu in the year 2010 plus n, right? So P sub 1 would be 2011, P sub 2 would be 2012. All right, give a recursive definition for P sub n. Okay, so if you know how many there were last year, how would you calculate how many there were this year? That is, how do you take a decrease of 40%?
So itself.
Itself, P sub n minus 1, yeah.
And minus.
Yeah. 0.4, you're very close, on the right track. 0.4 what? You can write 0.4 or 0.40, yeah. But it's this 40% of what?
Oh,
of Pn minus 1. Take the amount you had and subtract 40% of it. Right? Like if you have there's a $100 sweater, right, for 40% off, you take your $100 and you subtract 40% of $100. So you do 0.4 times 100. Okay. What is a quick shortcut instead of doing, say, 100 minus 0.4 of 100? What could I write instead that's just a little quicker? Yeah, you can just say, if I'm losing 40%, I'm keeping 60%. So I could just say 0.6 of however much I had last year. And the algebra bears this out also. This says 1 Pn minus 1 minus 0.4 Pn minus 1s would leave me with 0.6 Pn minus 1s. Yeah, so my numbers are a little bit different. You must have had a 30% decrease, right? So this is my, there's my formula. Yes. So they did 0.7, meaning if we're losing 30%, we're keeping 70%. Okay. All right, and then for B would be an explicit description. Okay, so if we're keeping only 60% each year, then I would say, well, I'm starting with 900,000 cases, right? So I'm starting with 900,000 cases of the flu. And then the next year, I'm only going to have 60% of that. So I multiply by 0.6. And the next year, I'm only going to have 60% of that. And the next year, I'm only going to have 60% of that. And the next year, I'm only going to have 60% of that. So I'm multiplying by 0.6 over and over and over again. Each year, you take 60% of what you had before. What do you use to represent repeated multiplication? A power. Yeah. So I put my n up there to indicate that I'm multiplying by the 0.6 repeatedly. Each year, you keep 60% of what you had before. So you're multiplying by 0.6 each year. So there's my explicit formula. 0.6 is the common ratio. Yeah. 0.6 is the common ratio. It's all, I like to, instead of calling it a ratio, I often call it a multiplier, right? 0.6 is the multiplier. That's what you multiply by. So that, are you going to switch the wording on that? Of course not. No. No. They didn't even use that word in this problem, right?
No, but 9.37 did one.
Yeah, they should put several earlier when you did the example problem. They would talk about finding the
what the common ratio, okay. Yeah, in a linear growth problem, when you always grow by the same amount, that's called a common difference. This is exponential because you're multiplying, and we call that the common ratio. The common ratio is the thing you multiply by, and the common difference is the thing that you add in a linear problem. All right, so if the trend continues, how many new cases of equine flu will be reported in 2025? So I'm looking for P sub what? 15, yeah. So I can use my explicit formula, 900,000 times 0.6 to the 15. And then we just put that in the calculator. And you can just type it in directly. You don't have to do anything special. Almost every calculator, I'm pretty sure that all of you have a calculator that knows the order of operations. So you can type in 900,000 times 0.6 x to the y 15. If you don't have an x to the y button, you might just have a little caret or a little hat that means exponent. So after 15 years, cases of equine flu should come down significantly to only about 423 cases. Sure. Yep. This one, number 6?
Yeah.
Okay, in 2010, the number of mathematics majors at a certain university was 425. In 2011, the number of mathematics majors increased and it was 478. What is the growth rate as a percent from 2010 to 2011? All right, well, how much did they grow by? How many more students are there in 2011 than in 2010? Yeah, so I'm just going to subtract 478 minus 425, 53 more students. Okay, so I have 53 more students. So my total change is 53 students. Okay, so I want to know what percent change this represents. So this is a really good skill to have, to know what people mean when they say percent change. Like, in the news, you'll talk about, the deficit went up such and such percent. Like, what does that mean, right? So a percent change is always the amount of change, the total change, and then we compare that, right? Because you need something to compare it to, because if I make $10,000 a year and I get a $1,000 a year raise, that's a significant amount, right, to someone that makes $10,000 a year. But if I make $1 trillion a year and I get a $1,000 a year raise, like, I don't even notice, right? That's so small. So you have to take your amount of change and compare it to what you started at, right? So we're going to take our total change and compare it to our starting amount. And that will give us an idea of the relative size of the change. And we express that as a percent. Okay, so my amount of change is 53. My starting amount was 425. And then when I do this calculation, 53 over 425, I get 0.1247. So that's a decimal that represents that fraction. Well, how would I write that as a percentage? 12.47%. And then we just should be careful to see if they gave us instructions on how to round here. It doesn't say. Let's see if it's in the answer. 2 decimal places. Yep. Yeah, so 12.47 is what you would type in there. Mm-hmm. Yep, they're using symbols to represent the amount of change. Y minus X is the amount of change, and X is your starting amount. Yep. Yeah. Yeah, so that's good. They're just using symbols to write what I wrote out in English. Any other homework things? Tons, okay.
I don't understand 90%. I know how to do it. I get the answer, but I don't know why.
Okay. Well, are there any that you want to go over? Okay, so we have we're given that the 685th Fibonacci number is approximately 6.4128 times 10 to the 142nd, which is just a giant number, right? Which is why we wrote it times 10 to the 142 instead of writing it out, because that times 10 to the 142 means take the decimal point and move it 142 places to the right. So if we were to write it out, there would just be, you know, lots and lots of zeros.
So it's a scientific notation, and that's something we're supposed to remember from when we were in school.
I covered it last class. I covered it last class. Okay. Okay, so we'll do this one together. Hopefully that will clear it up. Okay, so if we want to find an approximate value for the 686th Fibonacci number, we would say, okay, well, anytime you take a ratio of 2 Fibonacci numbers in a row, the bigger one on top of the littler one, we should get the golden ratio, 1.61803, which is approximate, right? So I'm going to put in F86 is what I don't know, so I'm just going to leave it 686. And then F685, I know that's 6.4128 times 10 to the 142. That should equal 1.61803. And then to solve this thing, you would like multiply both sides by that denominator. Or you can think of this as over 1 and cross multiply. Yep. Thank you. F686, thank you. Okay, so F686 times 1 is F686. And then I'm going to have 1.61803 times this number, 6.4128 times 10 to the 142. You're still writing what?
I'm trying to understand it.
Absolutely, yeah. So where did I lose you and what I did? All right, let's look at this first statement. This is one of the discoveries we made last class. Okay. Yeah, you take a ratio of Fibonacci numbers. When you're far out in the list, you get the golden ratio, right? Okay. So anytime you take a ratio of 2 big Fibonacci numbers that are next to each other, you get the golden ratio. All right, so then I just replaced. Now I'm just making a substitution, right? I took this 685, F685, and they told me what that was, so I just replaced it with its value. Okay, so then now I have an equation with an unknown in it. The unknown is F sub 686, which is a little odd. Like often the unknown is usually X or N, but I'm calling the unknown F sub 686. Yes, yeah. So if notation throws you, you could just put an X there and say I'm solving for X, right? And then I put the 1.61803 over 1 just because I like to solve proportions. But But you don't need to write an over 1 there. This is just a little, you can, to any number ever, you can put over 1,
So the
right?
answer to our problem is what you just wrote below it.
Yes.
Well, that's easy. I mean, I thought we were actually the real answer, not just
So this is the answer. Now, all I have to do is simplify that number a little bit. Okay. So I can, when you multiply things, I'm just going to multiply these first two, and I'm going to leave this alone because that just means it's a giant number, right? So I'm going to just multiply my 1.61803 times 6.4128, and I get 10.376 times 10 to the 142. Again, this number is correct. That is the value of the 686th Fibonacci number, approximately. And that means you take your 10.376 and move your decimal 142 places to the right. Okay. But the rules of scientific notation, and like when I say rules, the convention of scientific notation. So when you're dealing with numbers that are really huge or really small, they have a ton of zeros, right? And you indicate how many zeros there are by a power of 10. So in order to be able to quickly glance at the power to get a sense of how big or how small that number is, we all follow the same convention that the number in front of it should be a number between 1 and 9, because then the exponent gives us the most information. Nothing? Okay. Okay. No, it's okay. It's okay. I want to make it clear. Okay, so let's pretend that I'm a scientist and I have some results from an experiment, and I say, okay, the results are 6 times 10 to the 34th power molecules or whatever. I don't know. And then Dwight will be another scientist, and his results, he says, oh, well, my results are 716 times 10 to the 33rd power, right? So if I want to compare the sizes of those two numbers, they're both gigantic numbers, right? They're both just huge, but one is bigger than the other. And the easiest way to be able to compare them is if I could just glance at the exponents, because that tells me how many zeros, right? But Dwight wrote his number, this number in front is 716, and this number in front is 6. So what I would want to do is convert Dwight's number so that the number in front is just a single digit like mine is. And I would write it as 7.16 instead of 716 times 10. So I just moved my decimal 2 to the left, right? So I need to increase my exponent by 2 to account for the fact that I moved that decimal place. So that would be 35. And now it's much easier to compare the two numbers. 6 times 10 to the 34 or 7 times 10 to the 35. 10 to the 35 is bigger, right? Whereas before, it wasn't as clear which one was bigger. So this is just a convention that has developed to help people compare the size of really big numbers or really small numbers. Yeah. In the green? In the pink. That says 716. And then I changed it to 7.16 and adjusted the exponent to account for that. It's true, it would be equal. So if I wrote 71.6, that would be 10 to the 34th. I would have to adjust the x. Because everyone just agreed. The scientific community.
I'm disagreeing right now. This makes any sense.
Because you want a single number in front.
I want a single digit in front.
What do you want to match?
Yeah. So we could have all agreed. Okay, hold on. So I don't care if the in fact, I don't want the exponent to match, right? Like, I want to be able to compare the size of really big numbers, right? So let's do a few where, let's say, so I have 5 times 10 to the 4th, and 6 times 10 cubed, right? Which number is bigger? The top one, because that's a 5 with 4 zeros after it, and that's a 6 with 3 zeros after it. 4 zeros is more than 3 zeros, no matter what number's in front, right? No matter what the digit is in front. So 5 times 10 to the 4th is the same thing. I could write that as 50 times 10 cubed, right? It's the same number, but it's much harder to compare the size of those two numbers when the first digit, if you use one digit versus two digits. So let me write another example. If I have 3 times 10 to the 6th and 15 times 10 to the 6th, which number is bigger? The bottom number, why? But yeah, so the 10 to the 6 are the same, and the 15 is bigger than the 3. Okay, so so if I write these same two numbers as 3 times 10 to the 6th, or 1.5, instead of 15, write it as a 1.5 times 10 to the 7th, can you tell now which number is bigger? The bottom one, because it's got more zeros. 10 to the 7th is much bigger than 10 to the 6th. Yeah, Emma? Yeah. What's different?
Because you have more places, allows, you have know that there's only one digit. That's all.
Mm-hmm.
You're keeping one digit.
So, yeah, yeah. So you want to be able to use the exponent to compare the relative size of the numbers. Bigger exponent, bigger number, right? Bigger exponent means more zeros, so it's a bigger number, right? So we all could have decided that the number in front, right? If I want to compare two numbers, we all could have decided to use two digits here, and as long as everybody did the same thing, it would be easy to compare. So everyone decided to use one digit. It's just the convention to make it easy to compare sizes of numbers. Yes. Yes, I will. Yep. Okay, so I have 10.376 times 10 to the 142. This is not in scientific notation yet, because this first number has to be a single digit, right? A 1 through 9, right? So to change this to a number from 1 through 9, I'm going to move the decimal 1 to the left. So I have 1.0376. Yeah, and that changes my power of 10 because I moved this to the left one. When I move it back to write the whole number, I have to adjust the exponent on the 10. So that's scientific notation. Yes. Yes. Yeah. All right, anything else do you want to go over from homework or otherwise? Okay, so this is our review for test 2. Test 2 is next class. So this is our review class, and subjects on the test covered are apportionment. We learned 5 methods. We learned something about the quota rule and the paradoxes that can occur in Hamilton's method. This will be the majority of the test. And by majority, I mean more than half. More than half. So like maybe like approximately 60% of the test. Okay. All right, and the remaining 40% will be divided between population sequences, which involves sequence notation, writing explicit and recursive formulas for linear growth models, exponential growth models, and logistic growth, I'm not testing you on. Okay. So this is what we learned about sequences. Notation, writing explicit and recursive formulas, linear growth models, and exponential growth models. Then we talked about the Fibonacci numbers and the golden ratio. You need to know the recursive rule for the Fibonacci numbers, what the golden ratio is, and what a golden rectangle is. Resources for the test. You can use a calculator. You can use the reference sheet that's on the first page of this packet and a one-page sheet of notes of your own creation. Let's look at the reference sheet to remind you. Sorry, it's pages 3 and 4. Reference sheet is page 7. Sorry, the reference sheet is page 7. It has a little summary of what the 5 apportionment methods are, what the quota rule is, and what the paradoxes are. And then it has the general formulas for linear growth, the formula for arithmetic sum, the general formulas for exponential growth, and some stuff about the Fibonacci numbers, the golden ratio, and golden rectangles. So you can bring this sheet with you to the test, page 7. And then you can also make an additional sheet, reference sheet for yourself. You can put anything you want on it. You can write on both sides of it. It can contain any material that is written or typed by you. That's the only restriction, is that you have to write it or type it yourself. Okay. No photocopying chunks of the book and shrinking them down and pasting them onto a piece of paper. So get a good night's sleep, show all your work, because work can earn a partial credit even if you're wrong. Right? Pace yourself, read the questions carefully. I believe there are like 5 questions with multiple parts each. You'll have an hour and 15 minutes, but it's written to be a 1-hour test. But if you need a little extra time, I won't kick you out. It's not a problem. Yeah.
Okay, so what are the problems that we do where you say we always have to show what F whatever is? What are the cases where we have to write with problems? The numbers that we started with. Got it.
Oh, writing a recursive formula. Yes, you need to give the seeds. Write a recursive form. Sure. All right.
So they increase by 4.
I've written a sequence on the board. April, you saw the pattern. They're always increased by 4. What kind of growth model always increases or decreases by the same amount? Linear. Okay, so that is something that I could ask you. I could put a sequence up and say, you know, what kind of growth is this expressing? And you would say linear. It is an arithmetic sequence. So the sequence is the result of linear growth. An arithmetic sequence is the result of linear growth. So this is linear growth. This is, or we could also say this is an arithmetic sequence. Okay, so if I want to write a recursive formula, so I'll just call this, I don't know, P sub n. So recursive formula, you're allowed to use the term or terms before the number you're trying to calculate, right? So if I want to calculate the nth term of this list, I would take the term right before it, which is P sub n minus 1. And what do I do to it? Add 4. And then when you're using a recursive rule, like if I wanted to calculate P sub 8, I would need P sub 7, right? So if you're using a recursive rule to build a sequence, you have to have at least one number to start with to apply the rule to. So you have to give the first number of the list as part of your formula. You could. Yeah, you could. You're right. You're right. You could. It just, again, it's just convention. If you're trying to be clear, you give the first number. Yeah. Yep. Yes. P sub 0 would be -1. Yeah. Yep. So if you were going to go backwards from where you started, you'd subtract 4 and you'd land at -1. All right, now let's want to write an explicit formula. I would say P sub n equals, now the only thing I'm allowed to use here is n. And you can usually build an explicit formula by knowing the recursive rule, right? The recursive rule is you add 4. So I add 4, add 4, add 4, add 4, add 4. Repeatedly adding 4 is what mathematical operation? Multiplying, right? Adding a number over and over is multiplication. So I'm going to say, well, I'm going to start with a 3, and I'm adding 4 over and over and over again, which is multiplying. However many times you add it, you multiply by n. So you start with 3 and you add 4 n times. Yeah. So if you have trouble reasoning it out, right, and coming up with 3 plus 4n, the other thing that you can do, right, as a stopgap measure to do well on the test, I would prefer, right, that you sort of have a conceptual way to build a formula. But on your little cheat sheet, there's a formula for the linear growth model, right? And it says P sub n equals P sub 0, your starting amount, plus your common difference, I'll just write CD for common difference, times n. Okay. So now you can just plug in the stuff, right? Now you can just say, okay, well, P0, my starting amount, that's 3. My common difference is 4 times n, formula written. Okay. So that's one way that you can just make sure that you do well on the test until it all starts to coalesce.
I have moments when I'm like, oh yeah, this makes complete sense.
Yeah.
And I just forget it because I go,
Yeah.
oh.
Yeah. And like I said, I'm not going to put a sequence that has some mystery rule on your test, like we did on the first day of Intro to Sequences. If I give you something to write formulas for, it will be linear or exponential. Just to point out, at the end of your packet, you do have a study guide, a list of things you should be able to do, and some sample test problems to use as practice. There are videos for all of these sample test problems. Link to them is in Moodle. Or you can just search for my channel on YouTube. They're all on YouTube. All right, so here's a sequence of equations, right? So normally we study sequences of numbers, but we've got a list of equations here. And these have to do with the Fibonacci numbers. It involves the Fibonacci numbers. So I'm just going to write down the list here. 1, 1, 2. And this is F1, F2, F3, F4. And the reason I'm writing these down underneath is because they asked me about subscripts in part B, and that's what you asked about. Okay, so a reasonable choice for the 5th equation in this sequence. So I'm just going to do the whole thing to make sure that everybody's on the same page. All right, 1 looks like the first number in every equation. So we have 1 plus 2, 1 plus 2 plus 5, 1 plus 2 plus 5 plus 13, 1 plus 2 plus 5 plus 13 plus 34. So let's look at these numbers. I have 1 and 2. Then I have 1 and 2 and 5. Then I have 1 and 2 and 5 and 13. Then I have 1 plus 2 plus 5 plus 13 plus 34. So the numbers in the list are the pink check marks, right? And so in my next equation, I'm probably going to have 1 plus 2 plus 5 plus 13 plus 34, because every list has everything from the previous. And then what would I add to that? 89. Skip over 55 and add the 89. Yeah, what does this add up to? 144. So you could just add these in your head or in your calculator and you'd get 144. Or you could try to come up with a pattern based on 3, 8, 21, 55, right? So I've got 3, 8, 21, 55. If I follow this pattern, 3, 8, 21, 55, the next one would be 144 because it's every other Fibonacci. Hold on. Okay, go ahead, April.
Do you expect us to write the whole, write down the reasons for just 144 and get
No, because I asked you for an equation. 144 is just a number. It's not an equation. Yeah. Yeah. So that is the fifth equation in the list of equations. All right. So if I wanted to find the subscript that would make the following equation true, well, look at the relationship between the last number in the sum and the sum, right? So I've got 2, 3, 5, 8, 13, 21, 34, 55. Those numbers are always, how are they related to each other in the list of Fibonacci numbers? They're right next to each other, right? I've got 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. So if my last number that I'm adding up is the 21st Fibonacci number, what's the sum going to be? F21. The number right after it would be F22. So the subscript there would be 22. All right, and so let's generalize it. If the last number I put in my list of numbers that I'm adding is the nth Fibonacci number, what's it going to add up to? The n plus first Fibonacci number. The next Fibonacci number in the list. Does that make sense? Okay. Oh, okay. So basically, this is just practice recognizing a pattern and expressing it using the sequence notation that we have learned. Yeah, Tyler. Yep. So if a golden rectangle has width 10, we want to find its approximate length. Yep. Let's call this L, right? A golden rectangle is just a rectangle where the longer side divided by the shorter side is 10, is phi. There's two ways to draw this rectangle because I was not clear when I what is width and what is length. So there are two possible answers, right? So I could have also drawn this as L and 10, right?
Could you use W? It doesn't matter, right?
Yeah, it does not matter. You use whatever letter you want. I used L for length because they asked for length, right? But you can use W. It's just a letter to represent what you're looking for. Yeah. So I was not.
Looks like width and
Yeah.
I mean, it's length and height more than width. It's like a depth.
Yeah. So yeah, don't let the words confuse you. It's a rectangle. Rectangles have two dimensions, right? You can call it base and height. You can call it length and width. You can call it length and height, whatever. There's two dimensions. One of them is 10. What is the other one? So whichever way you define it, right? Because it was not clear from the question what length, which is length and which is height, which is whatever, you know. So there are two possible answers based on the way the question is worded. In this case, 10 is the longer side, so I would say longer side divided by shorter side is the golden ratio, because I said it's a golden rectangle, right? And in this case, my longer side is L, so I would say L divided by 10 is the golden ratio. And you don't have to do it both ways. Whichever way you drew this picture would get full credit. It's fine. On the test, I think I actually drew the picture for you, right? So there's no interpretation. Have you found the length yet? Do you know the length of the other side? No, then that's not the answer. Okay, how do you find the length now? Yeah, I could write these as proportions, put the 1.61803, and you cross multiply. So this says 10 times 1 is 10, equals 1.61803 times the length, and then divide both sides by. So we get L is 10 divided by that. 6.18, okay. All right, and then over here, L times 1 is L, 10 times 1.61803. L is 16.18. So there's two possible answers to this question. Mm-hmm. So when I draw a rectangle, how do you know which dimension is the width and which is the length? It's usually labeled. Yeah, I didn't draw the picture for you, so I think it's ambiguous, right? If I draw this rectangle, what is the length and what is the width? Okay, so Emram thinks this is the length and this is the width. Anybody disagree?
Yes.
Yeah, see, it's ambiguous. Width is a bad word. We could just say that. Yeah. Yeah. So maybe it's not a good word, but you get the idea, right? Like I said in the test, I drew a picture for you, labeled one of them X, and said find this length. Yes. There's still two possible answers. Yeah. Yes, I could say that. Yeah. That would be more specific, yeah.
You reduce that to that widget.
The directions on the test will be clear, but whenever there's no rounding directions, 2 decimals is a good rule of thumb. Yeah. Yeah. No. Anything else?
Are there opportunities for us to get any extra points with that?
I don't think so. No. Okay, so we have a rabbit population in a field is being studied. When it was first counted, there were 100 rabbits. 1 year later, there were 140 rabbits. So if we assume linear growth, right? So you have to really key in on the word linear there. You assume linear growth. we want to find an equation, explicit or recursive, for P sub n. We'll do both just for the fun of it. Okay, so linear growth means that each year you're going to grow by the same amount, right? So if in year 1 we increased by 40 rabbits, then from year 1 to year 2 we again increased by 40 rabbits, right? So my list is going to be 100, 140, 180, 220, right? So linear growth means you're always growing by the same amount. So if you grew by 40 in the first year, you're going to continue to grow by 40 every year. So now if I want to write a formula, I would say P sub n, since this is linear, I could say, well, if I want to know the population in any year, just take the population from the year before and add 40. Right? And I should also tell you that the first year's population was 100. Right?
Plus the first.
That's the recursive formula.
That's W goes.
You can call it P0, that's fine. It doesn't matter. Nope. Just the first number in the list. Whether you start counting at 0 or at 1 is a personal preference. Okay, and now for an explicit formula, I would say, well, Pn is, it starts at 100, and I add 40 again and again and again and again, n times. So I start with 100, and I add 40 n times. So I wrote a recursive and an explicit. So according to the linear growth model, what will be P10 be? I can use my explicit formula and just plug in a 10. It would be 100 plus 40 times 10, which is 500 rabbits. So to interpret my answer, this says that after 10 years, 500 rabbits. Right, give some units and some words to explain what it means. Okay, so now we're going to assume the rabbit population is growing according to an exponential model. So you got to see that word exponential, right? Exponential means that you always multiply by the same number to get from one year to the next. So I should start by maybe writing out a few numbers, right? I know my first two are always 100 and 140, but to figure out the next one, right, because they told me there were 100 rabbits and then there were 140 the next year. But now my rule is multiplication, right? So what did I multiply by to get from 100 to 140? 1.4. How do you figure that number out? Yeah, how do you know that? Divide. Yeah, you can divide. You can do 140 divided by 100. That's why it's called the common ratio. You take the ratio of a bigger number to a smaller number, and that is your common ratio. That's the number you multiply by. So if you do 140 divided by 100, you get 1.4. That's your multiplier, right? So 100 times 1.4 gets me 140. Do it again times 1.4. That gets me 196. Do it again. 274.4. Don't ask me how there's 0.4 of a rabbit. I don't know. Okay. Right, yeah. So there's my exponential growth list. So I have the same two numbers in the beginning, 100, 140, but the rule that governed how I got from 100 to 140 is different. Instead of adding 40, I got there by multiplying by 1.4. Okay, so addition, linear growth, multiplication, exponential growth. So now I'm going to try to write formulas for this list. P sub n equals, if I want to write a recursive formula, I would say, oh, well, each number in the list is the number before it times 1.4. Yeah. And I should tell you the first number in the list is 100, right? And then my explicit formula, I would say you give the starting amount, start with 100, and then you're multiplying it by 1.4 over and over and over again, n times. How do you indicate times 1.4 times itself n times? To the n, yeah. This is recursive.
That's actually the answer for C. Correct?
Yeah, this is the answer for C. I just ran out of room.
So with linear, you're not using an exponent.
Right, linear, you won't have exponents. Yep, explicit has an exponent. And then, so for part D, if I want to find P10, I could take my explicit rule and plug in a 10. 100 times 1.4 to the 10th.
Okay, so an exponential growth model is not but it is.
Right, yeah. 100 times 1.4 to the 10th. 2,892.55. Yes.
Don't you get the 1.4?
1.4, yes. So I looked at the first two numbers in the list because those are the only two I was given, right? 100 and 140. And so between those two numbers and this word, oh, sorry, we're looking at C here. We have 100 and 140, that was given. And this word exponential. Those pieces of information are what gives you the 1.4. You say, okay, exponential means that I'm looking for a number that I use to multiply to get from term to term, right? So I had to ask myself, what do I multiply 100 by to make 140? And you can figure that out by going backwards. Do 140 divided by 100. So you take the ratio of these two terms, divide them. And 140 divided by 100 is 1.4, which means that 100 times 1.4 gives you 140. Does that make sense?
Yeah.
Okay, good. You're welcome. All right, what else? Anything? All right, so the Mitchell numbers are not a sequence that we have talked about before, but you know how to read a formula, right? So I told you that I wouldn't give you a sequence of numbers with a random formula and ask you to come up with the formula, and I will not do that. But I could give you a formula and ask you to write the list of numbers. That's much easier than taking the list and going backwards to the formula. Okay, so I've given you a formula here for something called the Mitchell numbers. They're actually related to the Fibonacci numbers, and you'll see. Okay, so I've given you the seeds, M1 and M2, right? So I can start writing my list down. I know 1 and 2 are the first two numbers. And then the rule is that any number, let's try to just translate this to English. This says that any number in the list is 3 times the number right before it minus the number 2 before it. So I would say my next number in the list is 3 times the number right before it, 2, right? Minus the number before that, right? So 3 times 2 is 6, minus 1 is 5. And then my next number is going to be 3 times 5 minus 2. So that would be 13. Yeah, I gave you the first two numbers in the list. The very first, I said, these are the seeds. The first number in the list is 1. The second number in the list is 2. Then use this rule. Yeah. Yeah. So if I wanted to write down the work for how I got that 5, I would say, okay, M3, the third number in the list, is going to be 3 times M2 minus M1. And you know what M2 and M1 are because I gave them to you. That's why when you use a recursive rule, you always have to give the seeds. So you have something for it to grow from. So this is 3 times 2 minus 1, which is 5.
So what is the n greater than 3 represent?
So the subscript is n. N is the subscript, right? Right there. So I already gave you sub 1 and sub 2. And then this says use this rule for any subscripts 3 or bigger.
Oh, got it.
Yeah.
But there are problems we've had in our homework where you said, I think that's what I'm thinking of it. 13.1.
Mm-hmm.
Greater than or equal to numbers, and you're supposed to do some equation that.
It's probably like this. It's probably a recursive rule, right? Where I say, let's say I'm going to give you B1 is 4 and B2 is 6, right? If I write a recursive rule where B sub n, the nth Fibonacci, the nth number in the list is twice the number right before it plus the number before that, right? I would say you can only use this rule. You can't use this rule to calculate B1 or B2 because there are no numbers before it, right? So you can only use this rule for subscripts bigger than or equal to 3. That's all that means. That's when you use the rule. That says 4. No, it didn't write well. So just for the fun of it, let's calculate B3 here, according to this rule. So this says when my subscript n becomes a 3, right? Then I would do 2 times b sub n minus 1. So if n is 3, this would say b sub 2. 3 minus 1 is 2. Minus b sub, when n is 3, if I replace this n with a 3, I'd have 3 minus 2, which is 1. So this is 2 times 6 plus 4. So 12 plus 4 is 16. Next number in the list will be 16. So that's how the Mitchell numbers work. And if I continue to write them out, let's see, 3 times 13 is 39, minus 5 is 34. You might already notice 1, 2, 5, 13, and 34. That's every other Fibonacci number. Right. If we do one more, 3 times 34 is 102, minus 13 is, I hope, 89. So we didn't do the first 10, but good enough. And then if I want to compute successive ratios, this is exactly what we did with the Fibonacci numbers. So take the 2 numbers that are next to each other and divide the bigger by the smaller, and you get 2. 5 divided by 2 is 2.5. 13 divided by 5 is 2.6. 34 divided by 13. 2.615. And if you keep doing this, these are going to approach 2.618. And that is just phi plus 1, 1 bigger than the golden ratio.